comical paradigms. How to move away from the all-too-common idealizations of Einstein's general relativity, which often leads in certain extreme and experimentally unverifiable sectors to absurd values worthy of the most comical singularities. A theoretical and experimental approach is proposed here for a deconstruction of the strong equivalence principle between gravity and acceleration. To accentuate the contrast, a cheeky contextual humor appears at
8 minutes 41 seconds.
But do not miss the main explanations. General relativity in the context of space-time and gravity is an extraordinary computational tool that allows for the study, research, measurement, and extrapolation of various astrophysical phenomena with very concrete values. However, enormous inconsistencies arise when these extrapolation values are pushed to extremes. For example, the refusal of the infinity of space-time by limiting our vision to our universe bubble originating from a mathematically idealized Big Bang with a starting volume of zero, while adding some absurd entities, for example, massive objects with zero volumes called black holes. Here, I criticize the zero volumes, not the enormous masses. Or even dark energy allowing to disregard the possibility of other external universe bubbles that could easily accelerate the observed expansion between distant galactic clusters. In a more general sense, the idealization of general relativity hinders the possibility of having a more realistic view of the universe around us and thus facilitates a reconciliation with quantum mechanics. But if it were only considered as an extraordinary computational tool applicable in areas where experiments have been able to confirm its validity, without wanting to blindly apply it to the entire cosmos, certain contradictions would not be troublesome and would simply allow to search for other explanatory paradigms more in line with observations and logic. Examples of inconsistencies defying the most elementary logic. The Big Bang is said to have started with zero volume, a behavior that some cosmologist mathematicians continuously infer in the first nanoseconds. However, there are several major problems. Just because we observe a relatively homogeneous expansion, does not mean that the origin of this expansion must be traced back to a zero volume. In fact, with these observations done billions years later, this origin could have the volume of a current galactic cluster, or even the volume of a pinhead. We wouldn't notice any difference. And obviously, thanks to a significantly more realistic, initial, volume, we can easily envision a previous local universe that contracted, compressed, and intersected to reach the current state. Have we ever asked ourselves what the maximum original volume of the Big Bang was, corresponding to the expansion and trajectories currently visualized by our astrophysical instruments? A small galactic cluster, a large one, several large clusters. These questions should not be avoided just because we idealize equations defined over a century ago, which work well in more easily quantifiable cases. Light deflection by gravity, measurable relativity of time, etc. A zero volume containing a massive object is impossible, and an experiment or observation proving otherwise has logically never been successful. So how is it that we try to fit an entire universe into it just because there is a vague common origin to the observed astronomical matter expansion and there would be mathematical coherence? Let's remember that mathematics do not define reality but model it, and when the modeling does not correspond, it needs to be adapted to reality. Note that the same reasoning, involving the fact that massive objects cannot occupy zero volume, applies to black holes, which then have a volume of unknown substance hidden under the event horizon. This is not an absolute event horizon, as it allows gravitational waves to pass through. A time zero before which there would be nothing, and from which an entire universe would emerge, is equally impossible. It is much more logical to consider the infinity of possibilities of movement, and therefore of time. Let's remember here that it is absurd to reject the infinity of space, contained entities, and time on the pretext that it could lead to almost infinitely improbable situations. Infinity is interesting precisely because it surpasses everything that is not infinite, including our ability to calculate certain probabilities that are almost or totally infinitely small. Also, let's remember that humanity has been familiar with the notion of infinity for a long time through monotheistic religions, which generally consider the deity as immortal and all-powerful. This, when taken out of the religious context, constitutes an interesting cultural familiarity with the notion of infinity. So, One might wonder why some scientists sometimes reject the so familiar notion of infinity, by dogmatically applying a secular system of equations that was not designed for it. Challenge to the strong equivalence principle. A principle observed between a homogeneous gravitational field and an artificially induced acceleration of the same magnitude outside significant gravitational fields. The strong equivalence principle is a direct Achilles heel of certain aspects of Einstein's general relativity, which may perhaps help discourage some exaggerated extrapolations while bringing relativity closer to quantum mechanics through the interpretative flexibility it would add. This Achilles heel in the form of the strong equivalence principle establishes an extreme connection between gravitational fields and accelerations. This principle can be illustrated by the observed physical equivalences between a small laboratory located in a rocket accelerating at 9.81 meters per square second and the same laboratory placed on the surface of the Earth under idealized conditions. No vibrations, specific noises or non-uniformity in the terrestrial gravitational field, which must of course have exactly the same numerical value as the rocket's acceleration. Observation happened from inside the laboratories without contact with the outside, and it's currently impossible in the state of science to determine in which context we find ourselves, even by conducting experiments on gravitation. The thought experiment is even more astonishing when one compares the completely free fall, no friction or collisions, in a perfectly homogeneous gravitational field with the act of floating freely in distant space without any significant mass nearby. Both cases imply a state of weightlessness, and in the current state of science, an identical small laboratory placed in either situation, without being able to observe the outside world or communicate with it, would not be able to discern the difference. General relativity is partially based on this assumed equality, but we are far from dealing with an equality because free fall is constantly accelerating, converting potential energy into kinetic energy, and if we can't measure the difference with the free floating distant space case, it's simply because each molecule, atom, and each of their constituents are accelerated with the same value and not restrained by obstacles. Therefore, no force appears between macroscopic groups of molecules, and we cannot measure anything in this way before a potential impact with the attractor. Nevertheless, the two contexts are very different, with a constant acceleration and accumulation of kinetic energy in one context and floating at zero or constant speed in the other context. It's hard to imagine more extreme situations, so we should say, we don't know how to tell the difference between these situations rather than there are no differences. In practice, it would be enough to detect gravitons, which are hypothetical particles associated with gravitational fields. Then the freely falling laboratory would detect many, while the laboratory lost in space would detect almost none, and then the principle of strong equivalence would crumble. This would thereby expose a flaw in the construction of the theory of general relativity, which could be reduced to a practical calculation method, but without its current pedestal that encourages the most extravagant extrapolation of numbers and calculations, while impeding theoretical investigations more in line with the reality of the physical world. Conclusion. Astronomy and cosmology would undoubtedly benefit from greater freedom in interpreting the general relativity theory, as many desire, including Harold Lesch in his video,
Die Relativitätstheorie nervt.
Corollary. There is a strong equivalence principle between your satisfaction and your willingness to subscribe for free to this channel. The considered action takes an infinitely short time over an infinitely short distance compared to the previously considered astronomical magnitudes. And here is at least 1 minute of music to facilitate your symmetrically invigorating action. for your attention.